Determine the equilibrium constant from initial concentrations and limited equilibrium concentration data. Complete a R.I.C.E problem. R.I.C.E stands for reaction, initial concentrations, change, and equilibrium concentration. The first thing we'll need to do is evaluate the change. The change is always going to be X. If it is a reactant, you are losing X from the thing you know the most about. If it is a product, you are gaining X. You'll then figure out how much of X is leaving all of the other reactants and being gained by all of the other products. You can do that using the mole bridge, the mole ratio from the balanced chemical equation as shown in the small dimensional analysis below. You can see that I've gone ahead and done it with both carbon monoxide and with methanol. And because I know everything about hydrogen, the hydrogen stays on bottom with its 2 moles. Notice we use negative signs to indicate that it is a reactant that is losing, being used up. And with products, they are positive because they are being gained. We are getting more of that concentration. After we know how much of X is being lost or gained by each of the components, we can go ahead and figure out what X is and apply it to all of them so that we can determine the equilibrium concentrations of each of our reactants and products. Here I've determined that 0.093 is X. This is how much concentration is being lost from the hydrogen. With the carbon monoxide, we're only losing half of that, and so what is left after we've lost 0.0465 from our 0.0750 molar concentration of the carbon monoxide is 0.0285. Since the methanol started with nothing, half X, the 0.0465, is what we will have at equilibrium for it. Go ahead and write down your equilibrium equation where you put your products on top, multiplying all of the concentrations together as they occur, and dividing by the product of the concentrations of your reactants all multiplied together. Notice that all of the coefficients from the balanced chemical equation will become powers. It's much more easily seen with things like the hydrogen where it had a coefficient of 2 and you can see that it was squared. We go ahead after we've got our equation and we can key in each one of our numbers. We can then go ahead and do the work and see our KEQ. That's really it. The biggest hiccup is figuring out what X is, take it slow, and then go ahead and figure out what X has done to all of your concentrations. Once you've got your equilibrium concentrations, it's the same old problem that you're used to with KEQ. For this one, we get 9.85 or 9.85 times 10 to the 0 if we want to be consistent with the way we normally look at KEQs.